Assalamualaikum dan salam sejahtera. So this is the topic of internal force convection. It's the last topic for force convection, convection heat transfer. So why we call it internal force convection? Because the fluid flowing in a bounded area. For example, it follows in the circular pipe, or it can flow in the rectangular duct. So because the fluid is bounded, so it under category of internal flow. So there is a bit different between external and external flow in terms of flow physics. That's why you have different chapter for internal flow and different chapter for external flow. So liquid or gas flows in the pipe or ducts commonly used in heating and cooling application and food distribution network. And the fluid in such application is usually forced to flow by a fan or pump through a flow section. So although the theory for this in fluid mechanics is reasonably well understood, but a theoretical solution obtain few simple cases. And then if you have a complex boundary condition, it's difficult to solve. Therefore, based on this problem, there are some experimental method have been conducted, and then we use the correlation, Nusselt number correlation, to solve the problem. All right. So in terms of internal flow, so we need to determine the mass flow rate. So based on this equation, the density, the average speed of the flow, and the cross section area. Then you can get the m dot. So the average velocity of incompressible flow in a circular pipe can be created by using this equation. But normally we don't calculate the V average. V average is given. Okay. And then for average temperature, in an the complete full distribution of temperature profile, so we looks like this. Okay. But it's difficult to determine so which temperature you want to use for analysis. So this is a T surface. Let's say T surface is higher than the T in the pipe. So due to the fully developed thermal boundary layer, it looks like this. And then you have a curve, which is the temperature is not the same from top to bottom. So it's difficult to choose which point temperature you want to use. So we take it as average temperature. Okay, basically T mean inlet plus exit divided by 2 is the temperature that we use for finding the thermal conductivity of the air or liquid, your Prandtl number, your heat capacity, and all parameters that related to your problem. This is calculation for the Reynolds number in internal flow. So D is basically if you're using a circular pipe, this is the diameter of the pipe, right? So this is the case for the Reynolds number for flow in circular tube. So this is the equation. You have m dot, you have the kinematic viscosity, pi, and your diameter. So for internal flow, Reynolds number less than 2,300 considered to be laminar. Okay. Larger than 10,000 is going to be terminal. So let's say you have four types of pipe. So circular pipe, square duct, rectangular duct, and channel. So if you want to calculate the Reynolds number for each of these case, you need to determine the hydraulic diameter. So if basically it is the effective diameter for you to calculate and plug in this Reynolds number equation. So because you have D over here. So for circular type is straightly simple. You choose the diameter. For square duct, you choose the length. Rectangular duct, the ratio of the length and the height. Okay. So basically, it is calculated from this equation. 4 multiplied by the area, cross-section area, divided by the perimeter. Okay. So this is, you can find this in the table in textbook. So this is important to for you in order to calculate the Reynolds number. So this is for internal flow. This is very important. Okay. Because we have originally initially we have average flow of V average. Okay, when it fully developed due to viscous effect, the boundary layer grows and then you have fully developed parabolic that look like this. So you have a entry region, a region where it starts to develop, and then you have a fully developed region. Okay, so why we want to study two condition? Because the heat transfer coefficient is a strong function of this boundary layer and thermal boundary as well. So in this case, so you have a heat transfer coefficient in this region is different compared to this region because of different behavior of fluid. So this is about to develop. This is region where you fully develop. So we call it a hydrodynamic interest region where it start to develop. Okay. So the hydrodynamic entry length is the length of the hydrodynamic interest region will start to develop, and hydrodynamically fully developed region, the length region remain the same. Okay, when it start to develop, and then the ballistic profile remain the same, your heat transfer coefficient remains the same. Same goes to the thermal interest region. So you start with the initially temperature. Every point is the same, and then due to the heat transfer, let's say the fluid is much more hotter than the bounded region. So you have this curve, okay, and then it start to develop and it's fully developed, okay. But the length between thermal and thermal interest region and hydrodynamic regions are different. So you have a different length. So in this case, this is a thermal entrance region where it start to develop, and then it's after develop, your temperature profile will look like this throughout the length. So this is thermally fully developed, and then fully developed region for thermal. So for hydrodynamic fully developed, the equation that can be used to distinguish the fully developed and before fully developed is basically the change of the speed in of r in x is 0, because you have the same temperature, sorry, not temperature, velocity profile, okay, in the x region. For thermally fully developed flow, the surface temperature, okay, minus the any temperature in the x, okay, divided by surface temperature at any point, and minus the mean temperature of this is equal to 0. This is the criteria to basically to know whether the flow in the channel has reached hydrodynamically fully developed or thermally fully developed region. So it's so important, okay, because it affects the heat transfer coefficient. So in entrance region, okay, initial start of it, so we have a high heat transfer rate. So let's say you have a problem, heat transfer problem. So at the early stage of the flow, that is the region where the heat transfer coefficient is high. Therefore, your heat transfer rate is high. But that is not so long. The entrance region is not so long compared to the total length of the pipe. And then you reach a fully developed region where you have a constant heat transfer coefficient. So high heat transfer coefficient, okay. If you have high heat transfer coefficient, you have high ability to remove heat, okay, or to accept heat. If you have low heat transfer coefficient, your heat transfer rate is going to be a bit lesser than the entrance region. Alright, so this is a general thermal analysis. Okay, assuming that your temperature exit is higher than temperature inlet. Let's say temperature inlet 25 degree and the exit temperature, let's say 30 degree. What causes the temperature to increase? Of course, you add heat in the system. You add Q in the system. So therefore, your temperature from 25 increases to 30 degrees. Okay, so in order to calculate how much Q you added in terms of watt, okay, you multiply the mass flow rate with the heat capacity of the fluid, okay, and multiply by the difference in temperature exit minus inlet. So you have Q dot over here in watts. So how much energy ideally you put in the fluid, which causes the temperature to increase from 25 to 35. Alright, this is the amount of heat in watts. If you want to calculate the surface heat flux, so in surface heat flux is a heat per unit area, basically watt per meter square. So after you done with calculating the heat flux, so done with calculating the heat, okay, Q, you can divide the Q, big Q, by the surface area internally. So let's say this is a pipe, so the internal surface area is pi dl. Let's say the L is 1 meter, so pi dl, and Q might divide by pi dl, and you have a watt per meter square. From that, small qs, okay, you can calculate the local heat transfer coefficient, or we are going to use the Nusselt number correlation to calculate the hx. So this is basically energy balance. So you added the q, so t increased from ti to te by using this equation or this equation. So cp, you can find the value based on the fluid you use in the appendix. Okay, so in this case, for this thermal analysis, we assume that we added we heat or cool the surface via heat flux on the surface. Right. So what happened on the temperature inlet? What happened on the temperature exit? And what happened on the surface temperature? So if we heat let's say this is a circular pipe, we heat the Q. If we heat the pipe by applying the heat flux on the surface, so we can also monitor the surface temperature. Of course, that is different. Heat with surface temperature. In this case, you add heat flux on the surface, and surface temperature will increase. But you don't know. But obviously we can calculate that, and then causes the inlet temperature to increase. So based on this graph, right? So let's say your temperature inlet start from here, and then temperature is going to be higher because we add Q on the surface of the pipe. So at entrance region, the T surface starts to increase because we add Q. T surface is the surface of the surface temperature of the pipe. Until it reaches fully developed region, the change between the surface and the temperature inside of the pipe, the fluid of the pipe, with respect to its length, remains the same. So delta Ts minus the red line, is going to be constant where you reach a fully developed region. Okay, therefore, the delta T is equal to T surface minus T mean. Okay, T mean is basically T of here, T average of here. Okay, is equal to Q dot S, the heat flux. Okay, divide by H. If you know the Ts, then obviously you can calculate the heat transfer coefficient internally. Okay, so initially this is the equation. You want to know how much heat you put in the system. So basically you calculate exit minus inlet, okay, multiplied by the heat capacity and the m dot. Okay, and next you can rearrange this equation, because this equal to the heat flux from the surface, okay, multiplied by the surface area, you get the big Q. So big Q is given from the temperature difference, and then it translates into the Q on the surface. Okay, in order to get the Q on the surface, you need to divide by ES, and then you get the QS. Rearranging this equation, okay, let's say you know the Q value is known. Rearranging this equation, you can get the temperature exit, okay, by this equation, okay, and the surface temperature you can get based on this form, this equation. If you know the heat transfer coefficient, normally we calculate the heat transfer coefficient by using the correlation of Nusselt number. Alright, so turbulent flow in tube. So let's say you are working with high flow, and then your Reynolds number is more than 10,000. So your Nusselt number that you need to use is this one. Very general Nusselt number, 0.023, Reynolds number to the power of 8, Prandtl number of n. So n depends on your problem. Let's say your temperature inlet is 25 and temperature exit is 40. Basically, there is a heating process, so your n going to be 0.4. If cooling process, let's say your inlet is 450 and your exit is 25, you use n equal to 0.3. So this is only for flow in tubes, not in duct. Flow in tubes for Reynolds number larger than 10,000. you use this. Yeah, you use this equation. Okay, let's look at some example. Mm. So water is heated from 10 degrees C to 80 degrees C by electric heater. We want to calculate the heat flux from the heater and pipe surface temperature. So we want to know the how much Q that we going to put in order to get 80 degrees C. Okay, and then what is the surface temperature of the pipe. So from this we determine the parameters for the parameters of for water. Looking at the table A9. Okay. What temperature you use? You use the average temperature 80 plus 10 divided by 2, 45 degree. So this is 45 degree. So you need to use, you need to take the density, thermal conductivity, kinematic viscosity, CP, heat capacity, and Prandtl number. The diameter is 0.2 meter. So the m dot is 0.0825 kilogram per second. So from here, you need to, for m dot, we need to change to calculate a v because we want to calculate the Reynolds number. So rearrange this equation, m dot equal to rho AV. Okay, you know everything, or you know all the parameters you have. So you calculate the V average, you get 0.2653, and then plug into a Reynolds number equation. So in this case, you choose your hydraulic diameter DH is equal to D because you're working with circular tube. And then your Reynolds number is 8,000 something. Okay, which is close to 10,000. Still can be used because we are working above 2,300 Reynolds number, so you can categorize this as a turbulent. And then you can use this correlation, Nasihat number, this as number, and your n is going to be 0.4. Why? Because we are heating from 10 degrees C to 80 degrees C. We are in heating mode. So starts with calculating the heat flux. So we use the general equation m dot Cp delta T. Okay, so m dot you know, Cp from the table. So temperature exit minus temperature inlet, and you have 24,150 watts. So this is the Q applied from the electric heater. So in order to find the Q, small q, which is a heat flux, watt per meter square, you need to divide that by internal surface area. Internal surface area of this, which the internal surface area equation is pi d L. So this is 13 a meter a pipe. Okay, this is 13 meter pipe. So this I didn't write in here. So basically this is 30 meter. And then you get the answer of the heat flux is 29.55 kilowatt per meter square. So any point of this, the heat flux going to be the same, 39.55. This is average. So in order to find the surface temperature, we need to find the heat transfer coefficient by using this correlation, Nasihat number correlation. Okay, so we use this one, and the n equal to 0.4 because of heating. We plug in all the related parameters that it requires. So basically, Reynolds number and Prandtl number. So this is Prandtl number. You get 56.85, and the Nasihat number is equal to h d over k. We rearrange this equation, okay, and then you get the heat transfer coefficient. Okay, this is the value of heat transfer coefficient. It's very high because of forced convection. Okay, then the inner surface temperature can be calculated by using this equation. So we use a big Q because you have A over here. Okay, you can also use this equation. Okay, but you don't have to use A because this is a heat flux. This is a heat. Alright, so plug in all the related information. So you have your H calculated from the Nasihat number. You have the Q, big Q, and then the surface area pi dl, and then T surface, okay, minus T exit. Okay, T surface minus T exit over here. Use this the end of the pipe, the information at the end of the pipe. So your T surface minus the T exit equal to the heat given to the system. So from the calculation you get a 96.3, which is makes sense because the surface must be hotter, and then because the surface is hotter than the flow of the pipe, and then the exit temperature will be hotter than the inlet. Alright, so this is another example. So we heat from 25 to 75. Oh, sorry, this is heated for, sorry, this 25 should be here, 75 should be there. Heated from 25 to 75, and have an average temperature of 50. Therefore, we find all the rated parameter for at the 50 degrees C. So in this case, all the parameters given. Okay, this is one step to calculate, to find all the rated parameters. So next step is to find the m dot. Okay, because we want to find q dot, big q dot. So m dot is equal to density, the area, cross section area, and the speed. Okay, you have all the information. You can calculate the m dot. Next, you want to calculate the big Q. Okay, by using m dot cp delta t. You have m dot, your cp from your table, your different temperature index and z 75 minus 25. You have 50,000 watt per meter square. Oh, sorry, 12,566 watt. Next, you want to calculate the small q, the heat flux. You need to divide the big Q with the internal surface area. Okay, the pipe is the diameter is 1 meter and the length of the pipe is 10 meters. So you have 40,000 kilowatt per meter square. So next, you need to calculate the Reynolds number. Okay, you have the density, you have the speed, you have the kinematic viscosity, and then you calculate the Reynolds number with basically 4,000. So this is more than 2,300, so we can categorize this as a turbulent, and therefore it allows us to use this correlation. For this problem, again, we are in a heating mode, so n equal to 0.4, and then you calculate the Nusselt number and equate this to Hd over K, because Nusselt number correlation is also equal to Hd over K. We have the K value from the table, we have the diameter of the pipe, therefore you can calculate the heat transfer coefficient. So in order to calculate the surface temperature, similar step, you use the Q equation. In this case, it uses the small q. If you use the big Q, you need to include surface area over here. If you small q, you don't have to include the A. So this is using a small q, heat flux, the heat flux. And then H you have calculated. So T surface minus T exit, and then you get the temperature 93.9. So in order to increase the heat transfer rate, okay, basically we increase based on this equation, okay, HA, so increase the area. So therefore we will find some pipe with an internal feed with the aim to increase the surface area or make the surface internal surface of the pipe to be rough. Okay, with the aim or goal to increase its transfer rate by increasing the surface area. Okay, that's all for internal force conversion. Thank you.